Hello everyone, welcome back to Diksha Karnataka YouTube channel. And in the midterm series today I am going to discuss a very important chapter, alternating current. Now from this chapter there is very highly expected numerical question will come in your midterm and obviously in your final exam as well. So don't ignore this chapter. This chapter theory portion as a theory is not super heavy, but from the questions are basically coming from the theory, the formulas that we are going to learn. So those formulas and equations are very important, and also you have to practice questions from this chapter. So everything we will be covering in the second video of this chapter. So without much delay, let me first discuss as usual what are all the important topics from this chapter. But before I start, I request you to subscribe to our channel if you have not yet done so, and also share this video along to your friends so that our subscribers can grow very quickly. Now let us look into the important concepts, DC and AC. The basic difference between DC and AC. AC applied to resistors. This chapter is alternating current, so only we will talk about AC on. And then we have phasors, basic representation of phasors. Then AC applied to inductors and AC applied to capacitors. We will learn them that as well. Then we will also be studying LCR series circuit, and lastly but not least transformer. So these are the important concepts from this chapter. So first we will discuss about DC and AC. So so far whatever we have learned, mostly we have learned about direct current. So whenever you see that there is a circuit like this, okay, a resistance is there and we have like this is called a DC circuit. Okay, so the source here is a battery or a cell, which is basically a DC circuit. Now what is the meaning of DC circuit? The meaning of DC circuit is that it can send a current only in a given particular direction. Okay, so the long arm represents positive, the small arm represents negative. So the current will always pass from positive to negative in normal circuits, right? So that's what we have learned in the current electricity chapter. Now so direct current is basically current that does not change its direction with time. Now no matter what, as long as the battery is connected, the current will always flow in the same direction. Okay, the direction of the current will remain unchanged, right? As long as the battery is connected, the current will always pass in this way. Now what if you can design a circuit where the direction of the current changes with time? So for example, if you have another resistor, okay, and you applied a new source, okay, the source looks like this, then what? Now in this case, the direction of current for some time it will be in this direction, after some time it will be in the opposite direction, and this cycle will continue. This is called alternating current or AC. Okay, alternating current or AC, current that changes its direction with the time. So the direction of current is not fixed, but it is changing with time. The current that we use in our day-to-day life, they are all basically AC or alternating current. That household electricity, the current that is coming from the power supplier and that you are using is basically alternating current or AC, right? Now here as you can see, the source symbol is different for AC, and the representation of AC is in using a term V is equal to Vm sin omega t. Okay, so as you know that sin omega t is not constant, it has different values for different angles. So as this term omega t varies, okay, the value of sine will change, and based on the particular particular value of sine theta, the corresponding V value will change. This is the value that we are measuring. Okay, and Vm is the maximum value of the AC. This is called amplitude of AC, and sin omega t is the term that changes its direction. So this is basically involved with the changing the direction. Now omega is the angular frequency. It is called angular frequency. similar to that of you learned in SHM. Okay, so basically a power supply, if it is dancing like an SHM, then we call it an alternating current, right? Now let's move on to the next part, AC voltage applied to a resistor. Very important concept. So this is an AC voltage. This is the symbol or representation of AC voltage. So V is equal to Vm sin omega t. Now if you apply this voltage, the corresponding current will be given by I is equal to Im sin omega t. Okay, now like we have done in Ohm's law, that V is equal to IR, that same principle is applicable in AC as well, even though the resistance term is more general in case of AC. We will see that in a while, but because only a resistor is used, okay, simple resistor and an AC source is applied across the resistor, then this current is given by Im sin omega t, and this is the amplitude of the current or maximum value of the current. Amplitude means maximum value. Okay, so the maximum value or amplitude of current is given by Vm divided by R. Okay, so maximum voltage divided by R will give you the maximum current in this case. Now in AC, the term power has very little importance. Only thing that we are interested is in average power. Average power is more important than regular power. Okay, V is equal to I square R or V is equal to P is equal to I square R or P is equal to V into I. So whatever formula you will use, okay, you will always get the same value. Now here you have to use not only I square R, you have to use this I. Okay, so I square R means Im square sin square omega t. Okay, so this is the normal average value. Now to find the average, you have to find the average of everything. Okay, now sin square omega t is average. Sin square omega t is average is half. This is a mathematical derivation. Maybe in future you will learn about it, but for now you remember that the average of sin square omega t or sin square any variable theta. Theta is not constant. If theta is variable, if it is a constant, definitely average value is 0. So if it is variable, then only average value comes into picture. So omega t, here omega t is variable because time is changing, right? Time is changing with every passing second. So the average value of sin square omega t is half. Okay, so if you put that value, you will get the average power. Now that average power can be written in this form. It is called Vrms into Irms, where Irms is nothing but what we have done, that average power is what? Average power is basically Im square into R divided by 2, right? So there is a 2 is coming. Now what we will do, we will write this as Im by root 2 whole square into R. Okay, this is how we write it. Now what is this? This is called RMS current. This is now a new thing which is defined as RMS current. So that our formulas that we have learned in current electricity, P is equal to V into I, P is equal to I square into R, the same formulas is here, but instead of maximum current or normal current, we are going to use a new current which is called RMS current. Okay, RMS current. Why RMS current? RMS current is basically representing the actual average of the current. Okay, so if I say 220 volt AC, 220 volt AC means that 220 signifies the RMS voltage. That 220 volt signifies the RMS voltage. You have to remember that. Okay, if I say the current that is 110 volt AC, 110 volt AC means 110 volt represents RMS voltage. Okay, most cases if I say something with AC, that represents RMS value. Okay, if I say 2 ampere AC, 2 ampere AC means it's the RMS current. Okay, and RMS is very easy to calculate. It is the maximum value of current divided by square root of 2, exactly square root of 2. Let's continue. with something we are calling phasor. Now AC is very difficult to represent. Okay, AC is not something very simple like DC. The graph was simple, the concept was simple. Now in case of AC, as you can see, AC is like a sin omega t graph. Sin omega t graph looks like this, and time is keep on increasing, right? If you start from 0 second, it will keep on increasing into infinity, right? Time is going towards infinity, right? Time is always increasing. Okay, it was few billion years since the world was created, and it will continue for another few more billion years. So time will keep on increasing till everything is destroyed, right? So if you want to represent AC and if you want to draw a diagram, then the diagram will be keep on going on like that. So that is very difficult and tedious for us to represent AC like that, this graph. Okay, normal static graph it's fine, but if you are representing with time, then this graph is actually very tedious, also makes no sense to keep on drawing the same graph again and again. So for that we have come up with a clever idea. The idea is that we will represent the AC using rotating vectors. They are called rotating vectors. So basically what happens is that based on the location of the this graph, okay, so this is V, this represents V, this represents current I at some particular time. Okay, so at that particular time, so we will represent V and I using arrows. So one arrow will represent V, another arrow will represent I. Now they can be on the same line, they can be at some other line as well, it does not matter. Okay, but they will be represented using separate arrows. Okay, their starting point will be same, they will have a common point which is the origin, and then it will rotate in this particular axis. Okay, so if you keep on rotating it, it does not matter whatever is the value of this, you can always find some rotation where this represents the position and value of I and V. Okay, so this is called a phasor diagram. Okay, phasor diagram has a lot of applications, especially those who will study electronics in electrical in future. Phasor diagrams have a very large role to play. So phasor diagrams are a very tricky and shortcut way to represent something which is very long. Okay, so here we have represented the voltage and current. Now if you see that voltage and current both are being represented by sin omega t, so here V and I both are falling on the same line. Okay, only the magnitude is different. Okay, for V magnitude, this arrow represents the magnitude of V, the direction represents where it is on the omega t graph. Okay, so this direction represents the position in omega t graph. So if you draw the omega t graph and if you point it, it will be the V direction of V, and then the I and V are actually in the same direction, only their magnitude is different. So that's why they are falling on the same line. For resistance, for normal resistance, they always fall on the same line. For capacitance and inductance, it is different. We will see that. In order to show phase relationship between voltage and current in an AC circuit, we use the notion. Notion means idea. Okay, idea of phasors. The analysis of an AC circuit is facilitated by the use of phasor diagram. A phasor is a vector which rotates about the origin with angular speed omega. So the angular speed of rotation is omega, that's why the omega term is called angular frequency or angular speed, right? So that's why we represents everything with this simple diagram, easy diagram. Okay, now let's continue with the thing, but before I continue, I have to mention you one thing. We have launched something new, which is KCET. It's a completely offline course where you can prepare for your KCET 2026 exam, and also you can prepare for Comet K 2026 exam. program. It is completely offline classes conducted across our Diksha campuses on weekends. So you can, if you want to book your seat right now, you can call on this number given on your screen, and our representatives will help you. They will try help you to understand what all is there in KC90 exam. Okay, so just call this number if you are interested. It is an offline program. It is a long term 90 days program. It will continue in phases. Okay, some part will be conducted before your board exam, then there will be a break, then again after your board exam some other part will be covered. So you can take a complete informed decision. If you are thinking KCET exam is easy, actually it is not. You can ask your seniors. For KCET exam you have to prepare hard, and if you are in Bangalore, if you want to take advantage of our experienced faculties, those who are teaching in all the campuses of Diksha, so don't wait, just call this number, take some inquiry how it can help you to achieve well in your KCET 2026 exam. The course is KC90. It's a 90-day program, so as you know, and it will be definitely worth looking at. Okay, Diksha is producing results every year, so this year also we are expecting to produce very good result. So for that, if you want to be part of this success story, definitely you have to enroll for this program. Now let's continue. AC voltage applied to an inductor. Now let us concentrate on what will happen if you apply AC voltage to an inductor. The current through an inductor is given by I equals to Vm by omega L cos omega t. So normally for resistor it was Vm by R. Now for inductor the equation changes slightly and it becomes minus Vm by omega L cos omega t, or I is equal to minus Vm by XL cos omega t. What is this XL? This XL equals to omega L is called inductive reactance. It is called inductive reactance. It is like resistance. Obviously its unit is ohm. Okay, it's like resistance but only in AC circuit. So this term XL is AC resistance of inductor. Okay, so inductor generally do not have any resistance in DC circuit. Okay, but they have something which is called reactance, which only applicable when it is connected in an AC circuit, and that reactance value is given by omega L. Very important term to remember. This term we will be using in case of solving numerical questions. Okay, now I is equal to Im sin omega t minus pi by 2. I is equal to Im sin omega t minus pi by 2. So this negative sign, if you want to incorporate, you have to adjust it little bit, and then you will get this I is equal to Im sin omega t minus pi by 2. In case of resistance, the expression was Im sin omega t. Right, in case of inductance, it is not simply Im sin omega t, it is Im sin omega t minus pi by 2. So as you can see, what was the voltage that we applied? The voltage that we applied was always same. Voltage, no matter whenever you apply, voltage is always same. So as you see that the angle for voltage was omega t, whereas angle for current is omega t minus pi by 2. So that minus pi by 2 term is extra. So and we can say that the current is lagging behind the voltage by an angle of pi by 2. What is the meaning of lagging behind? The meaning of lagging behind means that if you draw the phasor diagram, current will be always behind, so voltage will be always ahead. Okay, so whoever is in this side is ahead, whoever is falling behind is always lagging behind. So if you keep, and then that relation will keep on maintaining throughout the rotational time. Okay, if you keep on rotating this, after some time also the phase relation will hold. Okay, so basically you can say that this is, suppose this is voltage. Okay, so this is voltage and this is suppose your current. So they will keep on having this angle of 90 degree and they will keep on rotating like this. Okay, so the angle V will always lead, current will always lag. Okay, current is lagging because it is moving after voltage. Voltage is coming first, current is coming next. So that's why it is called current is lagging by an angle of pi by 2. So in a pure inductive circuit, current lags by an angle of pi by 2, which is very important to remember for MCQ and fill in the blanks question. Current lags by an angle pi by 2 in case of pure inductive circuit. Now average power in case of inductor is 0. So because sin omega t, in the last case we have seen that it was coming out to be sin square omega t, right? In this case it is sin 2 omega t. Sin 2 omega t, if you take the average value of sin theta, it will always give you 0. Okay, remember that average value of sin theta is always 0, average value of sin square theta is half. Okay, so average power in an inductor is 0, so it does not consume any power in AC. Inductor does not consume any power in AC. Now in case of capacitor, similarly we can do mathematics for a capacitive circuit in an AC circuit. So the current through an capacitor is given by I is equal to Vm divided by 1 by omega c cos omega t. Now this derivation is not part of your syllabus anyway. So I is equal to Vm by xc cos omega t. Okay, xc is equals to 1 by omega c is called capacitive reactance. It is called capacitive reactance. Okay, similar to that of inductive reactance. This is only applicable in AC circuit. Capacitors do not allow DC to pass through it. Okay, it only allows AC to pass, DC it blocks DC, right? Capacitor basically is a device which only allows AC to pass but it blocks DC, right? And its capacitive reactance is given by 1 by omega c. It is only applicable in AC circuit, and if you put this cos omega t, you will get sin omega t plus pi by 2. What was our voltage? Voltage is always same as I mentioned, V is equal to Vm sin omega t. So now the angle was omega t. For voltage, for current it is omega t plus pi by 2. So the current leads the voltage by an angle of pi by 2. If you draw the phasor diagram, you will see that current is coming before the voltage. In this case the angle is again 90 degrees, but current is coming first, voltage is coming next, and if you keep on rotating it, current will always lead the voltage. Current will always lead the voltage. Leading means ahead, lagging means behind. Okay, so lagging means it is falling behind, leading means it is always moving ahead. Okay, so current is always ahead of voltage in case of a capacitive circuit, whereas it is leading in lagging in case of an inductive circuit. These are very simple but tricky points to remember. And what about average power? Average power in case of capacitor, again it will be 0. Now LCR series circuit. Now if you connect R, C and L in series, okay, along with the AC source, then it is called an LCR series circuit. So previously 3 cases that we have learned where we have connected resistance, we have connected inductor, we have connected capacitor, but they are all alone, single. But if you connect them in series with an AC source, then it is called LCR series circuit. Okay, LCR parallel circuit is also there, but that is not part of our syllabus, so I am not discussing that. So LCR series circuit is connected like this. And what else? The major part that you have to determine is the whenever few resistances are connected in series or parallel combination, first thing what you do, you find the equivalent resistance, right? Resistances connected in series, we add the resistances. If they are connected in parallel, we take the reciprocals and add them. That's how we calculate the equivalent resistance. Similar to that, we have to find the equivalent resistance, but because it's an AC, we will not call it resistance, but we will call it impedance. Okay, so the term that we use in case of AC circuit is impedance, and the impedance can be calculated using this formula: Z equals to R square plus XL square minus XC square. Okay, sorry, there is a small mistake over here. Okay, XL minus XC whole square. Okay, same over here as well, XL minus XC whole square. So that's how we can calculate the impedance of the circuit. Okay, so the impedance of the circuit is given by R square plus XL minus XC whole square. Okay, so this is the formula for impedance in case of an AC series LCR circuit. Now this derivation is there in a geometrical format, but it is not important in your board exam. I am not discussing that derivation anywhere. If you are interested to learning about this derivation, you can mention in the comment below. Maybe I will incorporate that in one of my future video. This derivation is a geometrical derivation. Even if it comes in your midterm exam, I suggest you can ignore that and skip that derivation. Okay, but that is little tricky. If you make small mistakes, there is a possibility that the entire answer will be incorrect. Okay, so the impedance is given by R square plus XL minus XC whole square. Okay, the order does not matter, but I like to write it in this particular order. Okay, as you can see, there is a whole square outside, so XL minus XC or XC minus XL, both are same. In case if you see that XC is coming out to be bigger than XL, then you can use XC minus XL, otherwise XL minus XC whole square will be perfect. Okay, the current given in the circuit is the maximum value of the voltage applied divided by the impedance. That's how you can calculate the maximum value of current IM. Okay, so basically IM is Vm divided by R square plus XL minus XC whole square. So this formula is very important for solving numerical questions. What else? Now if XL is equals to XC, if you have designed a circuit with a particular frequency in mind such that XL becomes XC, then the term in the previous case that we have learned, this XL minus XC, that will be 0. Okay, so this term will be 0. So the entire circuit will be only resistance, right? So you can call the entire circuit becomes resistive in nature. Capacitance and inductance, they are cancelling each other kind of. So that type of circuit is called resonance circuit. Okay, that is called resonance in LCR circuit. So in this case, the current in the circuit becomes maximum, the power becomes maximum. Okay, this condition is called resonance if the corresponding angular frequency is omega naught. Okay, omega naught is the angular frequency, then omega naught L is XL and 1 by omega naught C is the XC. So from here you can calculate the angular frequency. Also you can calculate the normal frequency. Now normal frequency, what is the relationship between normal frequency and angular frequency? You have to remember omega is equal to 2 pi f. F is the normal frequency. Okay, omega is angular frequency, f is normal frequency. So basically what you can say that frequency is omega by 2 pi. Okay, so from here you can say that f naught is basically 1 by 2 pi square root of LC. This is the resonance frequency. This is called resonance frequency. If they ask you calculate resonance frequency, then omega naught, calculating omega naught is not sufficient. You have to calculate f naught. Okay, and this formula is also very handy. It will come handy whenever you are solving questions. Okay, many cases this frequency f will be given and you have to apply this conversion formula to convert it into angular frequency, because many cases angular frequency is important, because omega C, omega L, if you see that they are actually omegas, right? So if you want to apply XC equals to omega 1 by omega C, right? So in terms of frequency it will be 1 by 2 pi FC and XL will be 2 pi FL. So this is how you convert it into from normal angular frequency to normal frequency. These are very handy formulas for your problem solving. Okay, most cases, most problems, f will be given to you. F value will be given to you. You have to use these formulas to convert it into impedances. Okay. Now phase difference normally is given by phi is equal to XL minus XC divided by R. Okay, and this phi can be written as I is equal to Im sin omega t. In case of resonance, phi becomes 0. In case of resonance, this phi becomes 0. Now if you plot the graph of current versus frequency, you will see that at a particular frequency the value of current suddenly increases and then it keep on decreasing. So this value is called the resonance frequency. This is a resonance frequency. Now in the past, nowadays you guys do not use it. When I was a kid, it was very common to have a radio in our home, and we used to tune the radio using a device. Okay, there is a rotating device. If you rotate it, you can tune it your radio. Okay, FM radio, normal radio, whatever radio, and that point of time the TVs was not super common when I was a kid. We used to listen to the live match commentary through our radios only. So in that case so this radio actually utilizes this resonance phenomena. Okay, so they have a particular resonance frequency. If you can match that resonance frequency, each resonance frequency represents a particular radio channel. Okay, and your radio is designed such that it can resonate with that particular frequency, and that radio channel will be broadcasted to your home. Okay, so LCR they have a lot of other applications as well, but that was one of the simplest application of resonance. Okay, let's move on. Power in an LCR circuit. So as we have discussed, we have seen power in normal resistive circuit, we have seen power in normal inductor and capacitor, both are 0. But what about a power in LCR circuit? So power in LCR circuit can be calculated like this, and as you can see, the average power in LCR circuit can be given by Vrms into Irms into cos phi. Okay, so Vrms into Irms into cos phi. Okay, this cos phi is called power factor. This cos phi is called power factor. This cos phi was not present in case of the normal DC circuit, right? So this is something which is new, and that's why it is called power factor. It determines if there will be power, how much power will be consumed in the given circuit. Now to calculate phi, what you have to do, remember the formula. Phi is XL minus XC by R. There will be numerical questions where they will ask you calculate power factor. So first you have to find the phi, and then you have to use that phi to calculate cos phi. Okay, this is how you can calculate. Next, what? Let's see some of the points. So resistive circuit. If the circuit contains only pure resistance, it is called resistive. In that case, phi is equals to 0, cos phi is equal to 1, and the maximum power dissipation happens. Okay, purely inductive or capacitive circuit. In pure inductive or pure capacitive circuit, the circuit contains only an inductor or capacitor. We know that phase difference between voltage and current is pi by 2, therefore cos phi is 0, and no power is dissipated even though current is flowing in the circuit. This current is sometimes called as wattless current, because it does not consume any power, it does not consume any watt. That's why it is called wattless current. And the power factor for pure inductive and pure resistive both are pure inductive and pure capacitive both are 0. Not for pure resistive. In case of pure resistive, power factor is not 0. Power factor is 0 only for pure inductive and pure capacitive circuit. Now in case of series LCR circuit, the power dissipated is given by P is equal to Vrms Irms cos phi, where phi is tan inverse XL minus XC by R. So phi may be non-zero in an RL or RC or RCL circuit. Even in such cases, power is dissipated only in the resistor. So in case of a series LCR circuit as well, also power is only dissipated in resistance. Inductor and capacitor does not consume any power. Power dissipated at resonance in LCR circuit is maximum. Okay, so this is again, the circuit is effectively a resistive circuit. L and C's effect, they cancel each other, so circuit becomes effectively a resistive circuit, and power consumed in the circuit becomes maximum. Okay, now let us look into the last concept of the day, that is transformers. Transformers basically is a application of electromagnetic induction that we have learned in our previous chapter. Okay, so here we have a frame like this, frame like structure. One end of the frame we have something called primary, and on the other end we have something called a secondary. Now based on the nature of the transformer, okay, the number of turns in primary and secondary varies. Okay, usually there are two types of transformer. One is called step up transformer, another one is called step down transformer. Now step up transformer is something which increases the voltage, AC voltage, and transformer is only applicable for AC current, it is not applicable for DC current. Okay, this much you have to understand. And step up transformer is something where the voltage can be increased. Okay, by decreasing current, if you can increase the voltage, then it is called a step up transformer. Whereas if you do the opposite, that is you decrease the voltage, increase the current, then that is called a step down transformer. So when the voltage is transferred from power station to our homes, there are a lot of stages, and transformer plays a very important role while transmitting power. So when power station is transmitting, power is transmitted at a very high voltage, very low current, and but at a very high voltage. Okay, so it is transmitted to some local power station, local power grid. That power grid again now reduces the voltage and increases the current, and that current is finally again reduced near our homes. If you have seen that near your home, if you have seen some power transformers, sometimes they get burned, and you have to wait entire day. There was no electricity because transformer is burned, so they need to replace the coil inside the transformer. Okay, so transformer is something which is using like this kind of structure, that and this coil can burn. You have to replace it in case the coil gets burned. Okay, for many purposes it is necessary to change or transform an alternating voltage from one to another greater or similar value. This is done with a device called transformer using principle of mutual induction. Okay, now there is a relationship between the voltage and the number of turns. Okay, so this is the voltage of secondary, this is voltage of primary. So voltage of secondary divided by voltage of primary is number of turns in secondary divided by number of turns in primary. Same thing, Vs by Vp equals to Ns by Np. Okay, so this is the relationship, this is the conversion factor. If it's some small numerical question do come, then you have to answer it using this formula. Okay, but you have to remember that the power input is equals to power output. Power input is given by Ip into Vp, and power output is given by Vis into Vs. So power is equal always. So in case of ideal transformer, input power is always equal to output power. In case of real transformer, output power is always less than that of input power. You cannot change the power, you can change the voltage, you can change the current, but power will remain same, because power is related to energy. Energy will be conserved, right? Ideal transformer means no power loss is happening in a transformer, right? Now in a transformer usually there are few types of losses happens. Okay, you can learn about few losses, but losses are not super important. Four types of losses are generally there: eddy current loss, okay, flux leakage loss, and heating loss. Okay, so they are the main loss. You can remember the names in case you see some 2 marker or 3 marker question coming from that portion, you can answer them. Okay, so with this I will like to end this rapid revision. I will be back with the 2, 3, 5 marker question. There will be not many questions, mainly numericals we will be solving for this chapter. Numericals, I do recommend solving numericals from this chapter, because the formulas that you have learned, based on the straightforward formulas, you can solve numerical questions from this chapter. I will be back very soon. Till then, bye.